Welcome to the 7th lecture of electric circuits. In this lecture, we are going to see about the filters. So basically, we have 6 types of filter: low pass filter, high pass filter, band pass filter, band stop or band reject filter, notch filter, and all pass filter. So what is filter? Filters are the frequency selective networks. Means these are the networks which selects the desired frequency. So here Vi is input and V0 is output. This input can be written in S domain and J omega form, and similarly output voltage can also be written in S domain and J omega form. The input have fixed amplitude but its frequency is variable. So the transfer function of the network is given by Hs, which is also equal to output voltage upon input. As we have studied earlier, that transfer function is the ratio of output to input, and in this case it is voltage, therefore we can also call it voltage gain. In S domain it is written as this, and in frequency domain it is written as this. So basically we replace S by J omega. Okay, so our first case is low pass filter. What is the low pass filter? Those filters who pass all the frequency below the cutoff frequency, but it blocks or stops the frequency greater than cutoff frequency. So this is our ideal low pass filter. It has a specific cutoff frequency, but practically cutoff frequency is not specific. It decreases gradually. The area where frequency is less than cutoff frequency is known as pass band. Why? Because this band is only passed through the filter. And area where frequency is greater than cutoff frequency is known as stop band or attenuation band. Why? Because those frequencies are blocked and they do not pass through the filter. So this orange one is the practical graph of second order low pass filter. For first order it is in green. You can see the difference here. This cutoff frequency depends only upon the R and C. So now see some characteristic of a practical filter. Practical filter means the cutoff frequency is not specific, it decreases gradually. So the cutoff frequency of any filter can be adjusted as per our requirement by suitably selecting the numerical values of R and C component. I've just told you this. An ideal filter has a sharp cutoff characteristic like this, and a practical filter cannot have such a sharp cutoff characteristic since the frequency response of such filter is limited by its time constant. Therefore, any practical filter has gradual cutoff. So practical filter have gradual cutoff characteristic, and these cutoff characteristic may be approached to those of ideal filter by increasing the order of filter. See, this green one is the first order practical filter, and on increasing its order we are approaching to the ideal one. This can also be done by increasing the number of stages which are being cascaded. Means we have seen how the cascaded network are. So if we increase the number of stages, like this is our low pass filter 1 and this is our low pass filter 2, and similarly if we add the stages, means if we connect filters like this, then also it will at least approach to ideal filter characteristic, but it will not exactly attain its feature. Why? Because ideal is practically not possible. The gain during the pass band can be adjusted using the RC section. Okay, so this gain, this value can be adjusted by using the RC section, and therefore such filters are then called active filters. Now case 2 is high pass filter. High pass filter is just opposite to low pass filter. So here all the frequency are passed which is greater than cutoff frequency, and all the frequency are blocked which is less than the cutoff frequency. Therefore this is called pass band, and now this is called stop band. This green one is the characteristic of ideal high pass filter. and this blue is the characteristic of practical high pass filter. As we know that in practical case there is no sharp cutoff, therefore its characteristic is decreasing gradually like this, but for ideal filter it has a sharp cutoff. Now band pass filter. So band pass filter is a combination of low pass and high pass. It allows the frequency below the cutoff frequency omega 2. Therefore in this case it acts as a low pass filter, and it allows the frequency above the omega 1. So here it acts as a high pass filter. This filter passes only a particular band of frequency. So frequency less than omega 1 is stop band, and frequency greater than omega 2 is also stop band. But frequency between omega 1 and omega 2 is our pass band, because this is the only band which is passed. Ideal filter is shown in green and practical in blue. As you can see that the cutoff frequency are not sharp for practical filters. This range omega 1 to omega 2 is also known as bandwidth of the filter, and its value is omega 2 minus omega 1. So example of band pass filter is series RLC circuit, and the minimum order is 2. You will understand this order concept in control system. And we have seen that the bandwidth of series RLC circuit is R by L radian per second, and in hertz it is R upon 2 pi L. Now our fourth case is band pass filter or band stop filter. Again it is a combination of low pass filter and high pass filter. How? It passes the frequency which are less than omega 1. So here it is low pass filter, and then it passes the frequency greater than omega 2. So here it is a high pass filter. Therefore it blocks a certain band of a frequency. For ideal filters its cutoff is sharp, but for practical it is decreasing and increasing gradually. And now in this case, this area between the cutoff frequency is known as stop band, and the area less than omega 1 or greater than omega 2 is known as pass band. Example of band pass or band stop circuit is parallel RLC circuit, and also the minimum order needed here is 2, and the difference between these two frequency is called bandwidth of the filter. And for parallel RLC circuit we know that bandwidth is 1 upon RC in radian per second, and in hertz it is 1 upon 2 pi RC. Okay, so now this is notch filter. Notch filter is actually a band reject filter or band stop filter, but in these cases a whole band of frequency was rejected, but in notch filter only a particular frequency omega n, which is also known as notch frequency, is blocked. So a notch filter is further a special case of band stop filter, where a single frequency called notch frequency is not allowed to enter in the system. Such filters are used in the input of any audio system where 50 Hz, which is the main supplied frequency, is not allowed to enter in the system to minimize the noise or the distortion in the system. Such filters are also used at the input of any system to minimize the third harmonic distortion. How? We will set its notch frequency equal to the frequency of the third harmonic, and so this is how we are going to reduce the third harmonic distortion in our system. Okay, so now our last case is all pass filters. These are very simple, it passes everything, so they are called all pass filters. Such filters passes all the frequency component. As you can see, it's a straight line with constant gain. Gain is constant, but various frequency components are subjected to different amount of phase shift. The angle of the frequency component gets changed, and the minimum value of the phase shift is 0 degree here, and maximum value is minus 180 degree. Such filters has zeros in RHS, means if we plot in S domain, then zeros will plot here in this side and poles in LHS means poles will be plotted in this side. Okay, one thing here to notice that poles are plotted by using cross sign and zeros are plotted by using circle signs. Okay, now let's have this example that you have this type of transfer function which is s minus 1 upon s plus 2. So here zeros means numerator and denominator means poles. So here 0 is put this is equal to 0. So s minus 1 is equal to 0 means s is equal to 1. So this is our 0, and then if you put denominator is equal to 0 means this, then you will get s is equal to minus 2. So this is our pole. And now if you plot this, so s is equal to 1 will be here, and since it's a 0, so we are making circle, and s is equal to minus 2 is a pole, so it is plotted here. As you can see that zeros are in RHS of this line and its pole is in LHS. So this is the characteristic of all pass filter. You will understand this pole zero concept in control systems. Okay, now let's take an example. So this is our first order all pass filter, and here you have to find the transfer function of the network. Transfer function means HS means output upon input. Then pole zero pattern. I have told you this about the pole zero pattern. It would be like this because it is all pass filter. And then you have to find the magnitude response means value of this transfer function, only value versus frequency. And then phase response means angle of this transfer function with respect to frequency. So you have to find all these four things. Okay, this circuit may be a little bit difficult for you because it has this op amp. Many of you know this concept, but for those who don't know, you can have this brief introduction of this op amp. So op amp is basically short form of operational amplifier. So this is op and this is amp. The voltage at the input terminals of op amp are always equal because any ideal op amp has infinite voltage gain. Okay, so this is our op amp, and what is its input voltage? This is not its input voltage, guys. Input voltage is this one. And for ideal op amp, these two are equal because ideal op amp has infinite voltage gain, and in lab this gain is around 15,000 to 20,000. You don't have to remember this. Just remember that these two voltage are same. The input current drawn by the op amp or operational amplifier is 0 since any ideal op amp has infinite input impedance. See, input impedance means impedance seen between these two terminals, and for ideal op amp it is infinite, means it is open circuited ideally, so no current will flow here. So current I which is flowing here is equal to 0, and similarly here also all the current coming from here will go in this direction, and similarly here it will go like this. Nothing will flow here because it has a high input impedance. Always write KCL equation at the input of the op amp, means you will write the KCL equation at this node or at this node. So basically here you will write. Never write KCL equation at the output of the op amp, means you will not write KCL equation here at this node unless it is terminated by some load impedance. Means if there is some load impedance like this is RL, then only you can write the KCL equation here. Under no load condition, the output of op amp is arbitrary and is unknown. Means at no load its value is random and it is unknown. Therefore we don't write equation at the output, we write equation from input nodes. So this is a brief introduction of this op amp. Now we will solve this question. Now let the voltage at this node is V And since here also the voltage would be V, why? We have just studied this. And let us assume that the current I is flowing in this direction and here in this direction, and you know that current flowing in op amp is 0 because it has infinite input impedance. So we will write KCL equation at this node 1 and this node 2. So KCL at node 1 means here V minus VI upon R means current flowing in this direction, plus V minus V naught upon R means current flowing in this direction, plus current flowing here, which is 0. So the sum of all these are 0. Therefore, we get our first equation, this. Now we will apply KCL at node 2. So V minus VI upon R means current flowing in this direction plus current flowing in this direction. What is the current flowing in this direction? V upon its impedance, and its impedance is 1 upon SC. So V minus 0 upon 1 upon SC plus II, which you know is 0. Therefore, we get the value of V in terms of VI. Now we will put this value of V here. So from 1 and 2, we get this, and now we will take VI common, then we get this. So basically V naught upon VI, which is also known as transfer function, is equal to 1 minus SCR upon 1 plus SCR, and this is our required transfer function. So first part is complete. Now in second part you have to draw the pole 0 plot. So this is your 0 and this is your pole. So put 1 minus SCR is equal to 0. We get S is equal to 1 upon RC. So this is our 0, which is in positive side. And now put this pole equal to 0 means 1 plus SCR equal to 0. We get S is equal to minus 1 upon RC. So this is your 0, and this pole is your pole 0 plot. It was easy. Okay, now we will draw its magnitude and phase response. So this was our transfer function, and we put S is equal to j omega, then we will get this. Here its magnitude is this, and you can see that these two are same, therefore its magnitude is 1 irrespective of the frequency. It doesn't depend on frequency. Therefore we get a constant magnitude, and this is your magnitude response. And now angle of this transfer function, so its angle is angle of 0 minus angle of pole. So what is the angle of 0? It is this, minus tan omega RC. Why minus? Because of this minus sign. And then minus angle of pole, which is tan inverse omega RC. So therefore the total angle is minus 2 tan inverse omega RC. Now we will put omega is equal to 0, and we get the value 0 here. For frequency is equal to infinite, the angle is minus 2 into pi by 2, which is minus pi. So at frequency is equal to 0, angle is 0, and at frequency is equal to infinite, angle is minus pi or minus 180 degree. So this is a all pass filter where it passes all the frequency. Here the magnitude is constant, but phase is suffering some deviation from 0 to minus 180 degree. Okay, now we will solve this question. This is from ESE 2001. We have this transfer function, and you have to tell that what type of filter it is, and there are 4 options. So our transfer function is this, and in j omega form it can be written like this. Now put omega is equal to 0. On putting omega is equal to 0, we get h0 is equal to 0. So it doesn't pass any low frequency. Therefore it cannot be low pass filter, and it cannot be all pass filter. Why? Because all pass filter passes all the frequency. Now we will test for omega is equal to infinite. So we will put omega is equal to infinite. So here it is not possible to place directly, therefore we have taken this limit. So here we will take omega square common from both numerator and denominator. So we will get this, and on putting omega is equal to infinite we get this. 1 upon infinite is 0. Therefore 0 upon 1 plus 0 0, which is 0. So you can say it doesn't allow high frequency. Therefore it is not high pass filter. So the only option left with us is B, band pass filter. Therefore it is a band pass filter. So this is how you are going to check which filter it is. We will find the value at these two frequency and then investigate if any option is true. If there are two options, then we will further investigate, but it is rare, so we are limited to this only. Okay, now we have this question from GATE 2002. There is a first order low pass filter and the value of R and C are given, and then we have to find the frequency at which the gain of the voltage transfer function is 0.25. So gain of the voltage transfer function means the magnitude of the transfer function. And here from options we can see that the unit is in kilohertz, means you have to find F, not omega. So this is your first order low pass filter. You have to remember this basic first order low pass filter and high pass filter circuits, because it will be asked directly like this in exams. So this is your first order low pass filter, and this is your input, this is output, and this is the current flowing. So if we apply KVL here, then we get input voltage is equal to current into R plus 1 upon SC. Since this is open circuit, so therefore total current is flowing here, and you can see output voltage is the voltage across this capacitor, so it is I into 1 upon SC. Therefore the transfer function or the voltage gain or the voltage transfer function is V naught upon Vi, means output upon input, and you can see that I will get cancelled out, and similarly SC. Therefore we will get 1 upon SCR. Now we will convert this in frequency domain by putting S is equal to j omega. So this is your transfer function, and it was given the magnitude of the transfer function is 0.25. So its magnitude would be
1 upon under root 1 plus omega square r square c square.
And this is equal to 0.25. So we will now put the value of R and C as given in the question, and then we will solve, and we will get omega is equal to 15.49 into 10 to the power 3 radian per second. But here you have to be always careful that which type of frequency it is asking. It is asking in radian per second or in hertz. And from the option you can see that frequency in hertz is asked. Therefore we will divide this omega by 2 pi, and you will get 2.46 kilohertz. So option C is correct. And this is a frequency at which the gain of the voltage transfer functional filter is 0.25. Okay, so now we will see some basics of the first order low pass filter and high pass filter. We will compare between these two filters. So as we have seen in earlier question that this is the circuit of your low pass filter. This is your input voltage and this is your output. If we interchange the location of R and C component, means if you change the location of this and this, you will get here this. So this is the circuit of high pass filter, and the transfer function of low pass filter is this, where omega C is the cutoff frequency. And if we replace S by omega C by 1 upon S by omega C, then we will get the transfer function of high pass filter. So here 1 upon 1 plus 1 upon S upon omega C. So S upon omega C upon 1 plus S omega C is the transfer function of high pass filter. Okay, here remember that this is not omega C. I have written here omega, and this is small c, means subscript. This is your cutoff frequency in this case and in this case also. It is not written omega into capacitor. And now cutoff frequency. Cutoff frequency of both the filters are same, which is 1 upon RC, and then pole zero plot. So low pass filter have no zeros, you can see, and it has only pole which is at S is equal to minus omega C. But high pass filter has both zero and pole. Pole at S is equal to minus omega C and a zero at the origin. Then frequency response. So low pass filter will allow frequency less than cutoff frequency, and since it is not IL filter, therefore we are getting this gradual decrease. And here you can see that cutoff frequency is that frequency where the value becomes 0.707 of the maximum, means 1 upon root 2 of the maximum. And then we have high pass filter. High pass filter will allow the frequency greater than cutoff frequency, and since it is not ideal, therefore we will get this gradual increase. And the cutoff frequency is the frequency where the value is 0.707 of the maximum value. So this was your first order low pass and high pass filter. And by knowing all the basic differences between these two filters, it is now easy to remember its circuit and all other characteristics. So this was all about filters. If you have any query, then you can comment below. We will continue this subject in further lectures. Thank you.